I mean, think about a mathematical model, right? No matter how sophisticated it is, no matter how many billions of parameters it has, or how much compute you throw at it, it can't actually fundamentally surprise you.
Right, because it can only answer the precise question you ask it.
Exactly. It operates strictly within the boundaries of the assumptions you give it. Like, a model can't just wake up and question its own premise.
Hmm.
But data, specifically when it's viewed through the lens of human visualization and, rigorous skepticism, that actually has the capacity to genuinely shock you.
Yeah, and that is sort of the core paradox of modern analytics, isn't it? We spend all this time obsessing over the models, the scaling, the algorithms, and we treat the actual data exploration as this tedious preamble.
Yeah, like it's just chore work.
Exactly. But the actual moment of discovery, that true aha moment that shifts a business strategy or breaks open a whole scientific field,
Yeah.
that almost always happens in the exploration phase, long before a formal model is ever trained.
And yet, if you are sitting at your desk right now, staring at a massive, incredibly messy data set, discovery is probably the very last thing on your mind. You're really just trying to survive the sheer cognitive load of it all.
Oh, absolutely. The information overload is so real.
We have all been there. The glow of the monitor, thousands and thousands of rows of data, headers that are just like incomprehensible acronyms. There's incredible value hidden in that digital labyrinth, but you are effectively locked out. It feels like staring at a wall of static.
It is a universally recognizable modern anxiety. I mean, the
Right.
information is literally right in front of you, but without the architectural framework to process it, it might as well be encrypted.
So welcome to the deep dive. Today we are breaking down that encryption. Our mission is to explore the fundamental architecture of the data science workflow.
And we're doing this from a very specific perspective, right?
Right. We are looking at this through the lens of a self-taught learner, someone who might have zero formal programming experience, but who really needs to master these skills for a modern professional role.
Mm.
Whether you're a business analyst, a researcher, maybe a data journalist.
Because these tools apply everywhere now. They aren't just for software engineers.
Exactly. And our grounding text for this exploration is arguably the definitive manual on the subject. It's called R for Data Science, second edition, written by Hadley Wickham, Mynton K. Arundel, and Garrett Grohlmand.
It's a foundational text. And what I love about it is that it doesn't just teach you syntax. I mean, syntax is cheap.
You can just Google syntax.
Right, you can look it up in the documentation anytime. What this book teaches is a philosophy of data. It provides a blueprint for how to think about information structurally.
And the antidote to that anxiety we just talked about, that feeling of being totally overwhelmed by a massive spreadsheet, is structure. You don't need to memorize 1,000 disconnected programming functions. You really just need to understand the loop.
The whole game, as the authors call it. Before we even get into the weeds of writing code, we have to look at the macro architecture of this workflow.
Okay, let's unpack this. If we map it out, it follows a very specific logical progression. And it starts with import, bringing the data from wherever it lives into your working environment.
Right, which might be a database, a web API, or just a local CSV file. And honestly, that is often the first major hurdle. In the real world, data doesn't just sit in pristine little files waiting for you to read it.
No, it's trapped in proprietary formats, or it's encoded with bizarre character sets.
Or it's hidden behind complex authentication protocols. Importing is really about breaching the wall, just getting it into the room.
Mm.
And once you have the data inside your environment, you move to the second phase, which is tidy.
And tidying is distinct from cleaning, which is a nuance I think a lot of beginners totally miss.
Yeah.
Tidying is about structural consistency. It's about coercing the data into a specific architectural shape.
Yeah, making sure the semantics of the data set actually match the physical layout in the computer's memory.
We will definitely dive deep into the mechanics of that later. But essentially, it's organizing the raw material so your tools can actually grip it.
Precisely. It's like you cannot operate a manufacturing plant if the raw steel is just dumped in a giant pile on the floor. It has to be loaded onto the assembly line in a very specific orientation. That is tidying.
Okay, so the steel is on the assembly line. What's next?
Once the data is tidy, you enter what the authors identify as the understand phase. And it's crucial to note this isn't a linear step. It is an iterative loop consisting of three main activities: transform, visualize, and model.
Right, so you transform the data by calculating new variables or maybe filtering down to specific groups. And then you visualize it to spot patterns or anomalies.
And then you model to answer precise mathematical questions. And you spin around that Loop transform, visualize, model over and over until you generate actual knowledge.
And then comes the final step, the one that, frankly, justifies the entire endeavor. Communicate.
Because an insight that exists solely on your local machine is completely useless. I mean, if you cannot effectively communicate your findings to a decision maker who lacks your technical context, the entire exercise was a total waste of time.
A waste of time and a waste of compute. And what is really fascinating about this entire workflow, import, tidy, the understand loop, and communicate is that the authors position programming not as a separate step, but as the medium in which all of this happens.
Programming is the water the fish swims in. It's the cross-cutting tool that scales your human intent.
But here is the brilliant, incredibly counterintuitive piece of advice the authors give to anyone trying to learn this workflow. They map out this highly logical, chronological sequence, starting with import and tidy, and then they explicitly tell beginners, do not learn the steps in this order.
Yeah, it's a profound insight into the psychology of learning. From a purely chronological standpoint, you obviously have to import and tidy data before you can visualize it. But from a pedagogical standpoint,
It's a nightmare.
starting a learner on data ingestion is a disaster. The authors note that 80% of data importing and tidying is deeply routine, mind-numbing work.
And the other 20% is navigating weird, esoteric edge cases that literally make you want to throw your computer out a window.
Exactly. It is the least glamorous, most frustrating part of the job. If your very first experience with programming is fighting with a broken date-time format from some legacy system, you are going to abandon the effort entirely.
The cognitive friction is just way too high, and the payoff is zero. You haven't learned anything about the world, you've just learned how to fix a broken comma.
The motivation curve just completely collapses. So the authors advocate for a completely inverted learning sequence. You start with visualization and transformation.
You give the learner data that has already been perfectly imported and perfectly tidied.
Right. You remove all that structural friction, and you let them immediately start generating visual insights.
You give them the quick win.
Yeah.
It makes me think of culinary school, you know? Like, if you want someone to fall in love with cooking, you don't make them spend their first month just practicing knife skills on thousands of onions.
Right. I mean, that's necessary for professional prep, sure, but it's soul-crushing for a beginner.
Exactly. You let them make a beautiful reduction sauce on day one. You let them taste the complexity they just created. And once they hooked on that result, they will willingly put in the hours to master the tedious prep work later.
Because they understand the value of the final dish. That's a highly accurate parallel. You build the intrinsic motivation first.
So when the self-taught learner eventually has to face the nightmare of ingesting a deeply corrupted real-world data set, they have the resilience to push through it.
Because they know exactly how powerful it will be once they get it into that understand loop.
I want to linger on that understand loop for a moment, specifically the interplay between visualization and modeling. We touched on this at the very beginning, the idea that models can't surprise you.
If we connect this to the bigger picture, this seems like a critical philosophical distinction in how experts approach data. They aren't just running algorithms blindly. They are using different cognitive engines for different purposes.
Yeah, they're using fundamentally complementary tools. Visualization is basically an extension of human cognition. I mean, we've evolved over millions of years to be unparalleled pattern-matching engines, specifically in visual space.
When you map data to a visual plane, you can instantly perceive clusters, gaps, and nonlinear relationships that would take pages of summary statistics to even hint at.
And because it's human-driven, visualization allows for serendipity. You might plot the data to answer question A, and the visual structure immediately tells you that question A is entirely irrelevant.
Right, and it shows you that you should actually be investigating this strange cluster of anomalies over in the corner instead.
Exactly. The visualization prompts the human to change the parameters of the inquiry. Models just cannot do that.
A model is an algorithmic construct. It scales beautifully. You can apply a model to 1 billion rows in a fraction of a second. A human can only look at so many scatter plots before their eyes just glaze over.
But the model is inherently constrained by its assumptions. Like, if you fit a linear regression model to a data set, it will give you the best possible straight line through that data. It will do it perfectly.
But it will never tap you on the shoulder and say, hey, this data is actually shaped like a U. A straight line is a terrible idea.
Right. It just blindly executes the assumption.
Which is exactly why the iteration is so vital. You use visualization to explore the unknown, to challenge your assumptions, and to refine your questions. And then, once you have a highly precise, bounded question, You hand it over to the model.
To confirm it, quantify it, and scale it. The two operate in this constant reinforcing dialogue.
So let's make that abstract idea concrete. If visualization is the optimal entry point for a beginner, how does it actually function mechanically? How do we translate raw tabular data into something the human brain can intuitively grasp?
Well, the book introduces a framework called the Grammar of Graphics, which is implemented in R through a very famous package called ggplot2.
The grammar of graphics, which was originally theorized by Leland Wilkinson, is a foundational concept. It moves us away from thinking about specific chart types.
Right, like saying, I need to draw a bar chart, or I need a scatter plot.
Exactly. Instead of that, it defines visualization as a structured process of mapping variables from your data set to aesthetic properties on a geometric canvas.
An aesthetic property being anything you can physically perceive. Position on an x-axis, position on a y-axis, color, size, shape, transparency.
You are essentially taking a column of abstract numbers and assigning them a physical avatar on the screen. Let's use the dataset the authors used to introduce this. It's the Palmer Penguins dataset.
Oh, the penguins.
Yeah.
A classic. It contains morphological measurements of 344 penguins collected at the Palmer Station in Antarctica.
Suppose we want to explore the relationship between the length of a penguin's flipper and its overall body mass. Under the grammar of graphics, we don't just ask for a scatter plot.
We define the structural mappings. We tell ggplot2 to take our dataset, the penguins. We map the flipper length variable to the x-axis aesthetic. We map the body mass variable to the y-axis aesthetic.
And then we declare our geometric object, or our geom, in this case, geom point, which represents each observation as a dot.
And instantly, a structure emerges. Every single row in your spreadsheet is now a coordinate in space. And the human eye immediately synthesizes those 344 individual points into a macro pattern.
You look at that plot and you see a distinct relationship. It's positive, it's roughly linear, and it's relatively strong. The points cluster around this invisible diagonal trajectory.
As flipper length increases, body mass increases. Big flippers, heavy penguins. It makes intuitive biological sense.
It's a very satisfying quick win. You took a wall of numbers and turned it into a clear, easily communicable truth.
But looking at this, though, I'd be worried that we're oversimplifying. I mean, we just drew a mental line through two variables. Are we missing hidden variables here? What if there are entirely different subpopulations within this data that are skewing that overall trend?
That instinct right there, that skepticism, is the hallmark of a good data scientist. Assuming a universal relationship between just two variables is incredibly dangerous.
It leaves you highly vulnerable to confounding variables.
Or phenomena like Simpson's paradox, where a trend appears in multiple groups of data but then completely disappears or reverses when the groups are combined.
So how do we interrogate that visually? We have our X and Y axes locked in. How do we test if this overall trend holds true across different types of penguins?
We leverage the grammar of graphics to add more aesthetic layers. We take another variable from our data set, let's say species, and we map it to a new aesthetic. We can map species to color.
Now, ggplot2 doesn't just plot dots. It evaluates the species column for every single row and applies a color mapping. Adelie penguins become red, chinstraps become green, gentoos become blue.
And suddenly, the visual narrative completely shifts. That one homogeneous cluster of points shatters into three distinct, separate subclusters.
You can immediately see that the massive penguins in the top right corner belong almost exclusively to the gentoo species, while the Adelie are clustered way down in the bottom left.
The relationship still holds. Bigger flippers mean more mass, but now you see it operates within the distinct biological parameters of each specific species.
You've added a whole dimension of complexity without adding any cognitive friction. However, the authors do emphasize a critical best practice regarding accessibility here.
Right, relying solely on color to transmit information is structurally flawed.
Because of color blindness. A significant portion of the population might look at that plot and just see a monochromatic blur where the red and green dots overlap.
If your insight relies on distinguishing those colors, you are failing to communicate. So you map the species variable redundantly. You map it to the color aesthetic, but you also simultaneously map it to the shape aesthetic.
So Adelies become red circles, chinstraps become green triangles, gentoos become blue squares. It ensures the visualization is robust and accessible, regardless of how the end user perceives color.
This entire process, formulating a question, mapping the aesthetics, spotting a pattern, doubting the pattern, adding a layer to test it, this is what we call exploratory data analysis, or ED.
And the book makes it very clear that ED is not a rigid checklist. It's an investigative mindset.
What's fascinating here is that it's an iterative cycle of curiosity. You generate questions, you search for answers through visualization and transformation, and those answers inevitably spawn more refined questions. You use the data to navigate the data.
Let's talk about the role of curiosity when looking at single variables, before we even start comparing things. The authors use a different data set to illustrate this, the diamonds data set, which contains attributes of over 54,000 round-cut diamonds.
If we want to understand just one continuous variable, say the carat weight of these diamonds, we can't use a scatter plot.
Right, because a scatter plot requires 2 dimensions. So for a single continuous variable, the foundational tool is the histogram. You map carat to the x-axis, and you use geohistogram.
The algorithm basically divides the entire range of carat weights into equally spaced intervals, or bins, and then simply counts how many diamonds fall into each bin, representing that count as the height of a bar.
It shows you the distribution, it shows you what is typical and what is rare.
Yeah.
And when you look at the histogram for diamond carats, it is immediately glaringly weird.
It really is. You don't see a smooth bell curve. You see these massive, towering spikes in the data at specific whole numbers: 1 carat, 1.5 carats, 2 carats.
But right below those thresholds, at 0.99 carats or 1.49 carats, the bars drop off a cliff. There are almost no diamonds at those weights, and then slightly above those whole numbers, the counts are huge again.
This is exactly where visualization serves as a profound trigger for curiosity. The data is screaming that something unnatural is happening. If diamonds were just rocks pulled from the earth and polished, you would expect a relatively smooth distribution of weights.
The structural anomalies, the spikes, and the asymmetric drop-offs suggest an external force. It's market psychology manifesting in physical data.
Precisely. To the naked human eye, a 0.99 carat diamond and a 1.00 carat diamond are visually indistinguishable. But the human desire for that round, whole number means the 1.00 carat diamond commands a significantly higher market premium.
So the diamond cutters, who are optimizing for profit, will intentionally sacrifice the cut quality or leave extra weight on the stone just to push it over that psychological threshold.
The histogram isn't just showing you the weight of carbon, it is revealing the incentive structures of human commerce. And this brings us to another critical aspect of EDA: how we handle outliers.
An outlier is just a data point that sits far outside the normal distribution, like finding a 5-carat diamond in a data set where the average is 0.7.
Right. And the instinct for a lot of beginners is to view outliers as a nuisance. They skew your averages, they mess up your axes, so the temptation is to just filter them out and delete them so the chart looks prettier.
The authors strongly warn against this. An outlier requires intense curiosity. You have to investigate the mechanism that generated it. Is it a data entry error, or is it a genuine discovery?
Did someone accidentally lean on the zero key when entering a price, or did you just find a completely new phenomenon?
I always think about the discovery of the ozone hole over Antarctica. The automated data processing systems initially flagged the drastically low ozone readings as outliers, as sensor errors, and just ignored them.
It wasn't until scientists manually looked at the raw data distributions that they realized the outliers were the most important signal in the entire data set.
That is the ultimate cautionary tale. You cannot automate curiosity. Visualization forces you to look at the shape of reality, anomalies, and all.
But, and this is a massive but, this entire magical process of visualization, of mapping aesthetics and finding hidden human behaviors, it is entirely dependent on the underlying structure of the data.
Right. If your data set is a tangled, chaotic mess, ggplot2 is completely useless. You can't map variables to aesthetics if the computer doesn't know what the variables are.
And this leads us to the silent industrial engine of all data science: tidying and transformation.
Here's where it gets really interesting. This is the phase that often breaks beginners, because it requires a profound shift in how you perceive information. We are very used to looking at data laid out for human consumption.
Reports, pivot tables, heavily formatted Excel sheets.
But data laid out for humans is almost always deeply hostile to computers. The authors frame this using an incredible literary analogy. They take the famous opening line of Leo Tolstoy's novel Anna Karenina: "Happy families are all alike. Every unhappy family is unhappy in its own way."
And Hadley Wickham adapts this into a foundational law of data science. Tidy data sets are all alike, but every messy data set is messy in its own way.
It is remarkably accurate. There are infinite ways to format a messy spreadsheet. You can have multiple tables on one sheet, color-coded cells that contain semantic meaning, merged headers, blank rows used as separators.
It's bespoke chaos. But tidy data adheres to a rigid, uncompromising architecture. There are three absolute rules for a dataset to be considered tidy in this paradigm.
Rule 1. Each variable must have its own column. Rule 2. Each observation must have its own row. Rule 3. Each value must have its own cell.
It sounds painfully simplistic. Variable equals column, observation equals row. But why is this specific, rigid structure the holy grail? Why does it matter so much to the underlying software?
It matters because of how R, and really any modern data analysis language like Python's pandas, interacts with the hardware of your computer. R is a vectorized language. Let's break that down conceptually. What does vectorization actually mean in this context?
Think about the difference between a master craftsman building a car by hand and a modern assembly line. In a non-vectorized approach like writing a basic for loop in older programming paradigms, the computer acts like the craftsman.
He goes to row 1, reads the population, reads the number of cases, calculates the disease rate, writes it down. Then it walks over to row 2, reads the population, reads the cases, calculates, writes it down.
It does this sequentially, one by one. It involves constant context switching.
Which is cognitively slow for the machine.
Exactly. But a vectorized language operates like the assembly line. A column in a tidy dataset represents a vector, a continuous block of memory containing the same type of data.
So when your data is tidy, you can tell R, take this entire vector of cases and divide it by this entire vector of population.
R doesn't loop through them one by one. It leverages the architecture of the processor to perform that mathematical operation on the entire column almost simultaneously.
It stamps out the calculation en masse. So tidying your data is essentially about aligning your raw information with the physical realities of CPU architecture and memory layout.
If your variables are scattered across rows and columns in a weird grid, you are forcing the computer to act like the craftsman, hunting around for the parts. If it's tidy, you feed it directly into the assembly line.
And the performance difference isn't just a few milliseconds. At scale, it's the difference between a calculation taking 2 seconds versus taking 45 minutes.
Furthermore, every package in the tidyverse, from Gigplot2 to the modeling tools, is built on the absolute assumption that the data coming in on the conveyor belt is structured this way.
So how do we actually fix the messy data? How do we organize the bespoke chaos into the tidy assembly line? The book details the mechanics of pivoting, and they use some famously awful real-world data sets to demonstrate this.
Oh, let's look at the World Health Organization tuberculosis data set. This is a classic example of data formatted for presentation, not computation.
It's an absolute nightmare. You load it up, and the first 2 columns are country and year. That looks totally fine. But then you have 56 subsequent columns, and the headers for these columns are things like CIPIAN 014, IPF 4554, and SNM 65.
To a human eye, or at least an untrained one, it looks like a corrupted file. But those aren't actually column names. They are data values masquerading as structural metadata.
The CMT indicates the method of diagnosis smear positive, the M indicates gender male, and the ISO14 indicates the age range 0 to 14 years old.
This completely violates the rules of tidy data. A column header should be the name of a variable, like diagnosis type or age group. Here, the actual variable names are hidden, and the values are smeared across the top of the table.
You cannot effectively run a vectorized operation to find the total cases for females because female data is fragmented across like 20 different columns. It's like having a messy closet where your shoes are mixed up with your coats and they're shoved into 50 different boxes.
To fix this, you use a function called pivot longer. You essentially grab those 56 wide columns and you pivot them down, collapsing them into long, neat rows.
You gather all those cryptic headers into a single new column called, say, demographic code, and you put all the underlying numbers into a column called cases.
You've lengthened the data set, but now every variable, country, year, demographic code, and case count has its own dedicated column.
And once you have that demographic code in a single column, you can use text manipulation tools to split CIPIAN 014 into 3 separate columns: diagnosis, gender, and age. Now you have a perfectly tidy data set ready for analysis.
And sometimes the chaos goes the other way. The authors bring up the CMS Patient Experience dataset, which tracks hospital survey results. Here, instead of being too wide, the data is too long.
You have a hospital ID, a survey question ID, and a score. But the hospital ID repeats over and over again for every single question.
Right. An observation in this context should be a single hospital, but the attributes of that single hospital are spread across multiple rows.
If you want to compare how Hospital A scored on cleanliness, versus doctor communication, you can't easily do it because those scores are sitting in different rows of the same column.
You're trying to compare row 5 with row 12 instead of column C with column D.
Precisely. So you reverse the process using Pivot Wider. You take the survey questions and pivot them out to become the new column headers, and you spread the scores underneath them.
You condense the rows until there is exactly one row per hospital. The structure now matches the semantics.
Okay, so through pivoting, we have achieved Tolstoy's ideal. The data is tidy, the variables are columns, the assembly line is ready. Now we have to actually do the work. Transformation, or what is colloquially known as data wrangling.
The toolkit for this in R is a package called dplyr.
dplyr is brilliant because it operates on a philosophy of verbs. Rather than having one mega function with 100 complex arguments, it provides a set of highly specific tools, each designed to do exactly one conceptual task to a tidy dataset.
The primary verbs are filter, mutate, arrange, and summarize. You use filter to operate on the rows, say, reducing a global dataset down to just observations from the year 2023.
You use mutate to operate on the columns, creating entirely new vectors of data based on existing ones, like creating a profit column by subtracting cost from revenue.
You use arrange to sort the rows logically, and you use summarize to collapse data down into summary statistics, like calculating the mean average.
But the true genius of the dplyr ecosystem isn't just the verbs, it is how you string those verbs together. And this is where the authors introduce one of the most transformative concepts for a beginner: the pipe operator.
The pipe, historically written as % greater than %, and in modern base are written as simply a vertical bar and a greater than sign. Why is this little piece of syntax so revolutionary?
Because it solves a fundamental cognitive problem in programming: nested functions. In standard mathematical notation or older programming styles, if you want to apply multiple functions to an object, you nest them inside each other.
If you want to filter a dataset, then mutate it, then summarize it. The code looks like summarize open parenthesis, mutate open parenthesis, filter open parenthesis data, condition close parenthesis, calculation close parenthesis, metric close parenthesis.
You have to read it from the inside out, navigating a labyrinth of opening and closing parentheses. It's incredibly hostile to human reading comprehension.
It really is. It forces you to parse the syntax before you can understand the logic. The pipe operator inverts this entirely. It takes the output of whatever is on its left and passes it as the first argument to whatever is on its right.
The authors tell beginners to explicitly read the pipe operator out loud as the word then.
And that single linguistic trick changes everything. Programming stops feeling like writing esoteric algebra and starts feeling like writing a recipe.
You write, take the dataset, then filter it for 2023, then mutate to calculate profit, then summarize the average profit by region.
The code flows chronologically from top to bottom, left to right. The cognitive offloading is massive. You are no longer translating logic into math. You are just writing sequential instructions.
It is deeply empowering. It bridges the gap between how we conceptualize a problem mentally and how we express it syntactically. Which brings us to the next massive leap for the self-taught learner.
We've manually tidied our data, we've wrangled it with verbs, we've visualized it, we found our insight. But in the professional world, data is rarely a one-off event. It is a recurring nightmare.
Let's say you spent 3 days writing the perfect script to claim the January sales data. And then your boss walks in and says, "Great work. Now do the exact same thing for February, March, April, and the entire archive back to 2018.
The brute force approach, which every beginner defaults to, is copying and pasting. You copy the block of code for January, paste it below, change jan.csv to feb.csv, and run it. And then you do it again for March.
And the authors are unequivocal about this. Copying and pasting code is a profound structural risk. It is a recipe for disaster. We need to transition from manually scripting tasks to automating them. We need to treat programming as a superpower.
This raises an important question. How do we know when to automate? The risk of copy pasting is what software engineers call incidental complexity or silent failure.
When you copy a 20-line block of code, you might remember to change the file name at the top, but you might forget to update a specific filtering variable buried on line 14.
So your February script is silently filtering based on a January date range. The code doesn't crash, it doesn't throw a red error message.
It runs perfectly, and it gives you entirely incorrect numbers, which you then put into a report for the executive team. That is terrifying.
It's the most dangerous kind of bug. To mitigate this, the book introduces a fundamental software engineering principle adapted for data science, the rule of 3.
If you find yourself copying and pasting a block of code more than twice, meaning you're about to create a third copy, you must stop, abstract the logic, and write a function.
You encapsulate the process. Instead of having raw code sitting out in the open, you define a custom tool.
What does the anatomy of writing a custom function look like for someone who has never written one?
It consists of three primary components. First, the name. And the author stressed that naming is crucial. It shouldn't be script to. It should be an evocative verb, like clean monthly sales.
Second, you define the arguments, or the inputs. What is the specific piece of information that changes every time you run this? In our example, it's the file path.
So you create a placeholder variable called file path. Finally, the body. You place your tidying and transformation code inside the function, replacing the hard-coded file names with your file path variable.
Now, when the boss asks for February, you don't copy 20 lines of code. You write one line. Clean monthly sales, feb.csv. The abstraction protects you from incidental errors.
If you realize you made a mistake in how you handle missing values, you don't have to hunt down and fix it in 48 different copy-pasted blocks. You fixed it once inside the function, and the fix automatically cascades to every month's analysis.
That is the leverage of programming. But we can go even further. If we have 48 months of data sitting in 48 different Excel files, even typing out that function 48 times is tedious.
This is where we introduce functional programming and the concept of iteration, specifically using a package called purrr.
Traditional iteration involves writing for loops, but the purrr approach feels much more elegant and aligned with the tidyverse philosophy. How does a beginner automate the ingestion of 38 separate files?
It's a beautiful sequential process. First, you need to tell the computer where to look. You use a base R function like list.files. You point it at your directory and say, find every file that ends in .xlsx.
The output is simply a vector, a list of 48 file paths. You now have an inventory of your raw materials.
Right. Then you use the powerhouse of the purrr package, the map function. The logic of map is simple but profound. Take a list and apply a specific function to every single item in that list, returning a new list of the results.
So we take our list of 48 file paths and we map the reexl function over it.
Exactly. In one line of code, R systematically traverses the list, opens the first file, reads the data into a data frame, opens the second file, reads it, and so on.
It handles the iteration automatically with no complex loop structures or indexing to manage. You end up with a list containing 48 loaded data frames in your computer's memory.
And then the final stroke of genius, the listbind function. You take that list of 48 separate data frames and you command the computer to bind them by rows.
Essentially smashing them vertically into one massive unified tidy data frame containing 4 years of data. You've automated the ingestion of an entire corporate archive in roughly 3 lines of highly readable code.
And beyond the sheer efficiency, this approach fundamentally shifts how you approach data cleaning. The book discusses a crucial mindset difference between beginners and experts here.
A beginner who writes a traditional loop will often try to do everything inside the iteration. They'll try to load the file, fix the column names, standardize the dates, and handle missing values, all before moving to the next file.
That sounds logical, though, right? Clean it as it comes through the door. Why is that an anti-pattern?
Because data is universally, relentlessly unpredictable. If you try to clean file by file, your code will inevitably crash on file number 17 because someone in that specific month decided to spell revenue with 2 V's.
Or format the date in a completely novel way. You get bogged down fixing micro errors in single files, missing the forest for the trees.
You fall into an infinite trap of edge cases.
Exactly. The expert approach, the holistic approach, is to do the absolute minimum during the iteration phase. Just get the data into memory. Read the files, bind them together into one massive, messy data frame.
Only then do you start cleaning. By combining first and cleaning second, you can view the anomalies in aggregate.
You can use your dplyr verbs to identify all the bizarre date formats across all 48 months simultaneously and write a single, robust transformation to handle them all at once. The overall quality and resilience of your pipeline improves drastically.
It's a profound shift in perspective. Don't fight the files individually, pull them all into the arena where you have the structural advantage. But this brings up an immediate, terrifying caveat.
Uh-oh.
This strategy of loading everything into memory and binding it together works brilliantly until it doesn't. Our self-taught learner is feeling incredibly confident. They've mastered dplot, dplyr, functions, and iteration.
They get their first major industry job.
And on day 1, the data engineering team hands them a data set that is structurally beyond the capacity of their local machine.
We have arrived at the frontier of big data.
The book uses a fantastic tangible example for this: the Seattle Public Library Checkouts dataset. It's a public dataset tracking every book checked out. It contains 41 million rows. It's distributed as a single 9 GB CSV file.
Now, a standard modern corporate laptop might have 16 gigabytes of RAM. The authors mention a widely accepted rule of thumb. To comfortably wrangle a dataset in R or Python without memory exhaustion, you generally need RAM equal to twice the size of the file.
Because the software needs space to hold the original data, space to hold intermediate transformations, and space to execute the calculations.
So if I try to use read CSV to open a 9 gigabyte file on a 16 gigabyte machine,
The machine's going to violently object, the RAM will fill up, the operating system will start desperately paging memory to the hard drive, the cooling fans will spin up like jet engines, and eventually the session just crash.
it is a hard physical limit. This is a moment where a beginner feels completely defeated. The tools they just mastered seem totally inadequate.
It's a paradigm shift. You can no longer rely on pulling the entire data set into local memory. The data is too heavy to move. Therefore, you must move the computation to the data.
And the book introduces an incredibly elegant solution within the R ecosystem, the Arrow package.
How does Arrow bypass the physical constraints of my laptop's memory?
Arrow allows for what is called out-of-core processing. Instead of using read CSV, you use an Arrow function called OpenDataSet.
When you point OpenDataSet at that massive 9 GB file, it does not try to load 41 million rows into your RAM.
Instead, it just casually peeks at the file. It scans the first few thousand rows to deduce the schema. It figures out the column names and determines if the columns contain text, integers, or dates.
It records this metadata, creates a connection to the file on your hard drive, and then it simply stops.
It builds a map of the data without actually picking up the data.
Exactly. It creates a lightweight pointer. And here is where it gets truly magical for the learner. You can take that arrow pointer, and you can pipe it directly into the exact same dplyr verbs you already know.
You can use filter, mutate, and summarize on this 41 million row object. When you execute the code, Arrow acts as an incredibly efficient engine in the background.
It reads a small chunk of data from the hard drive, processes your dplyr commands on that chunk, aggregates the result, throws the raw chunk out of RAM, and moves to the next chunk.
It streams the data through the memory rather than trying to swallow it whole. You get the result, say, the total checkouts per year, without ever exceeding your 16 gigabytes of RAM.
But the authors are quick to point out that while Arrow can technically stream a giant CSV, CSVs are fundamentally terrible formats for big data analysis. They introduce a format that every aspiring data professional needs to understand: the Parquet format.
Parquet. It's a term you hear constantly in data engineering circles. Why is Parquet structurally superior to our trusty old CSV file?
It comes down to how the data is physically written to the disk. A CSV comma separated values is a row-based text format. It is designed to be human-readable.
You can open a CSV in Notepad and read it line by line, but computers don't read like humans.
If you have a CSV with 100 columns, and you only want to analyze one column, say checkout date, the computer still has to read through the commas and text of the other 99 columns for every single row just to find the date.
It involves massive amounts of wasted disk reading. It's like having to read every single word on a page just to find the page number.
Look analogy. Parquet, on the other hand, is a binary columnar storage format. It is completely unreadable to the human eye.
But it stores all the values for a single column sequentially on the disk. So if you tell Arrow to analyze the checkout date column in a Parquet file, the computer goes directly to the physical location on the disk where that specific column is stored.
And reads only that data. It skips the other 99 columns entirely. It is hardware-level optimization.
And furthermore, because columns usually contain highly repetitive data like a year column just repeating 2023 over and over, Parquet can apply aggressive, highly efficient compression algorithms.
Like run-length encoding. That 9 GB clunky CSV file might compress down to a sleek 1.5 GB Parquet file. Queries that took 5 minutes on a CSV will execute in milliseconds on a Parquet file.
It completely changes the scale of what a single analyst can accomplish on a laptop.
This bridges us perfectly to the reality of enterprise environments. We talked about CSVs and Parquet files sitting on a hard drive. But if you walk into a Fortune 500 company or a major research institution, The critical data does not live in stray files on a local drive.
No, it lives in centralized, secured, massively scaled relational databases.
And the universal language for interacting with those databases, the lingua franca of data engineering, is SQL-structured query language.
Now, this introduces a serious point of friction. Our self-taught learner has just spent weeks mastering the elegant verb-based logic of dplyr and the pipe operator.
And now, to actually get data in a professional setting, they are told they have to go learn a completely different programming language with entirely different syntax and logic. That is a massive barrier to entry.
Historically, yes, it was a huge roadblock. You had to context switch constantly between writing SQL to get the data and writing R to analyze it. But the Tidyverse ecosystem provides a phenomenal translation layer, a package called dbplyr.
How does dbplyr bridge this gap?
It essentially acts as a real-time invisible interpreter. You establish a connection to the corporate database, and then you simply write the exact same dplyr code you've been using all along.
You take the database table, pipe it into filter, pipe it into mutate, pipe it into summarize. But when you execute that code, dbplyr intercepts it.
It doesn't attempt to pull the data into R. Instead, it translates your R code into a highly optimized, complex SQL query.
It writes the SQL for you.
It builds an abstract syntax tree of your logic and compiles it into the specific dialect of SQL required by that particular database, whether it's PostgreSQL, Snowflake, or SQL Server.
It sends that raw SQL query over the network to the database server. The massive multi-million-dollar database cluster does all the heavy computational lifting.
Executes the aggregations, and then simply sends the small, summarized final table back to your R session.
That is staggering leverage. A beginner with a laptop can query a billion-row table sitting on a server farm in another state, using the exact same intuitive syntax they used to count 344 penguins.
They don't have to be an expert database administrator to start extracting deep insights from enterprise data. It democratizes access to big data fundamentally.
So let's take stock. We've built the complete architecture. We imported massive out-of-core data from a database. We tidied it by pivoting.
We transformed it using automated iterated functions. We visualized the underlying human behaviors, and we modeled the precise mathematical relationships.
We found the truth. We found an insight that could pivot a company's strategy or change a scientific consensus. The job is done.
If you stopped there, the job was entirely pointless.
Right. Segment 6, the indispensable final step, reproducibility and communication. So what does this all mean?
This is where analytical rigor meets human reality. You can have the most elegant, highly optimized dplyr pipeline in the world, generating a mind-bending insight.
But if you cannot translate that insight into a format that a non-technical stakeholder can absorb and trust, your code is essentially useless.
Decision makers don't care about your vectorized operations or your Parquet compression ratios. They care about the narrative, the visuals, and the implications.
And historically, the communication phase involved a lot of friction. You would generate a plot in R, save it as an image file, copy it, open Microsoft Word or PowerPoint, paste the image in, and write your text around it.
Which breaks the chain of reproducibility completely.
Explain why that copy-paste workflow is so dangerous.
Because data is not static. Imagine you spend a week building a comprehensive Word document with 20 different copy-pasted charts analyzing quarterly performance. You send it to the executive team.
An hour later, the data engineering team emails you and says, sorry, there was a glitch in the data pipeline. The Canadian sales figures were missing. We've updated the database.
Oh no, your entire report is now mathematically invalid. If you use the copy-paste method, you have to go back to R, rerun the entire script with the new data, individually save 20 new charts.
Go back to Word, meticulously delete the old charts, paste in the new ones, ensure the formatting didn't break, and manually update any prose where you reference specific numbers.
It is tedious, error-prone, and soul-crushing.
To solve this, the book introduces a next-generation scientific publishing system called Quarto. It's an evolution of the concept of literate programming, originally championed by computer scientists like Donald Knuth.
How does Quarto merge the code and the communication?
Quarto fundamentally unites the narrative and the computation into a single cohesive source file. In a Quarto document, you interweave plain text prose, your explanations, your executive summaries, with executable blocks of R code.
When you hit the render button, Quarto runs the code in the background, generates the plots and the summary tables dynamically, and weaves those results directly into the final output document.
The code creates the report. So in that nightmare scenario where the Canadian data changes, you don't do any copying and pasting. You literally just click render again.
The code queries the updated database, regenerates every single chart with the new numbers, updates any inline text that dynamically references variables, and spits out a fresh, perfectly accurate report.
It makes your reporting infrastructure as robust and scalable as your analytical infrastructure. And what makes Quarto exceptionally powerful is its ability to tailor the output to the audience from that exact same source file.
Right. Because communicating with a fellow data scientist requires a very different level of transparency than communicating with a chief marketing officer.
Precisely. If you are sharing your analysis with a peer who wants to vet your methodology, you can configure Quarto to output an HTML document that displays all your raw R code, all the warning messages, and all the intermediate data transformations alongside the final plots.
It's fully transparent, but if you are presenting to the CMO, you simply change a few configuration parameters at the top of the file, you flip a switch.
You flip a switch, and Quarto suppresses all the code. It strips out all the technical scaffolding and outputs a beautiful, polished PDF report or an interactive web dashboard, showing only your executive summary, the final layered G2 visualizations.
The underlying truth is the same, but the presentation is optimized for the cognitive bandwidth of the recipient.
But underlying this incredible communication tool is a philosophical mandate that we really need to emphasize for the beginner: reproducibility. Quarto relies on the premise that your code runs perfectly from top to bottom every single time.
And the authors identify a psychological trap that almost every self-taught learner falls into regarding this. They state categorically, the R script, the physical text file containing your code, must be your singular source of truth.
Your source of truth is not the current state of your computational environment.
This is the most vital conceptual hurdle for a beginner to clear. When you are learning, you are highly interactive. You type a line in the console, you see what happens.
You load a data set, you click on it to view it, you tweak a variable, you run a filter, you gradually massage the data in the working memory of the software until that perfect visualization pops out on your screen.
You feel a massive sense of accomplishment. You save the picture and you close the program.
And you have effectively destroyed your work.
You have, because the environment, the working memory of the computer is ephemeral. When you close the program, the environment is wiped clean.
If you relied on your interactive clicking and typing to get that result, you cannot easily recreate it. A week later, when someone asks how you calculated a specific metric, you will stare at your script and realize it only contains half the steps.
Because the other half were done manually in the console and never recorded. You'll try to run the script and it will throw an error, because it depends on a variable you created interactively 3 days ago that no longer exists.
This isn't just an annoyance for beginners. This is at the heart of the replication crisis in major scientific fields. When researchers rely on manual interventions, undocumented Excel tweaks, or ephemeral environments, their findings cannot be validated by independent peers.
To combat this, you must adopt a discipline of strict reproducibility. The code must be able to completely reconstruct the environment from absolute zero.
How does a beginner operationalize that discipline?
By structurally organizing your projects. The authors recommend dividing your workflow into discrete, numbered scripts. For instance, 0-1 load and tidy are 0-2 exploratory analysis, R 0-3 modeling.
You must regularly practice restarting your R session, wiping the environment completely blank, and running your scripts from start to finish.
If you can start with an empty computer, execute script 1, execute script 2, execute script 3, and arrive at the exact same Quarto report every single time without human intervention, then your work is bulletproof.
You can zip that project folder, email it to a colleague halfway across the globe, and they can independently verify your truth. That is the threshold of professional data science.
This has been a massive architectural journey.
Let's trace the arc of what we've unpacked. We started with the sheer cognitive terror of a messy spreadsheet. We learned that the antidote is structure, the whole game loop.
We discovered that to sustain our motivation, we have to invert the learning process, starting with the immediate, visceral payoff of visualization.
We used the grammar of graphics to map abstract data to physical space, uncovering the biological realities of penguins and the psychological pricing of diamonds.
We explored the rigorous, uncompromising nature of tidy data learning, how vectorization and pivoting act as the high-speed assembly line for modern computation.
We adopted the dplyr verbs and the cognitive ease of the pipe operator, turning complex math into readable narrative.
We leveled up, using the rule of 3 and the per package to abstract our logic into functions and automate iterative cleaning.
When we hit the physical limits of our hardware, we learned how to wrangle big data, using the out-of-core streaming of Arrow, the hardware-optimized structure of Parquet files, and the translation power of Dudapplier to command massive SQL databases.
And finally, we wrapped our entire methodology in the rigorous, reproducible communication framework of Quarto.
It is a profound amount of complex material. But what is truly remarkable is that by approaching it structurally, step by logical step, an individual with no prior technical background can genuinely master this workflow.
They can transition from being overwhelmed by data to commanding it.
As we conclude this deep dive, I want to return to the philosophical distinction we started with. We spend immense amounts of time optimizing our code, writing efficient functions, and utilizing the massive computational power of databases to train models.
But as the authors of R for Data Science subtly remind us throughout the text, a model is inherently captive to its own assumptions.
It is an algorithmic machine that answers the exact question you ask, based on the parameters you define. It is fundamentally blind to the unknown unknowns. Only data, viewed through the lens of human visualization, rigorous skepticism, and relentless curiosity, has the capacity to fundamentally surprise you.
So the next time you find yourself staring at a massive, messy data set, do not rush to apply a model. Do not simply look for the answer you expect to find.
Build your assembly line. Keep your data tidy, map it to the visual plane, and actively look for the anomalies. Lean into the outliers. Let the data surprise you. You never know what profound truth is hiding in the architecture until you look at it the right way. Thank you for exploring with us on this deep dive.